Okay, here's the idea. I have this image here. You can see it's an arrow pointing up and to the left. There's little markers. Each mark is a millimeter. I'm gonna take this and light it up. Assuming I can figure out where to plug it in. Yeah, you get to see all sorts of weird things. That was probably the side of my face. And I'm then gonna put this towards a mirror. This mirror is a curved mirror. And this is it says both written on it, but this is a concave mirror with a 100-meter focal length. Now, what I'm gonna do is I'm gonna find experimentally where this image gets focused. I'll do this by putting this guy in, and I'll move it around. Until this is as focused as possible. What I see is I have an image. It's hard to tell. I thought maybe turning off the light would make it better, but now instead of pointing up, it's pointing down, so it's inverted. And also, if you compare, it's a lot smaller, so it's reduced. This image is also taking place right at 14.2 centimeters. This kind of shadow is making it, sorry, that's a lie, 14.7 centimeters, making it hard to see. That is the experimental value. I want you to find the theoretical value by making a lens diagram, using a ruler and working to scale. I'm also going to do this for moving the mirror 40 centimeters away from the light source. And then once I do that, finding the new image, which is right there at 26.6 centimeters. It is still smaller and still upside down. And I'm going to do it again for the mirror 50 away from the value. This is even smaller, and it's happening at about 37.2 centimeters. Now those distances are distances from the light source, which is not necessarily what I'm looking for. I'd be wanting to find the distance between the mirror and the image, but I will subtract and give those values. Okay, part B of the lab. We're gonna look at the same light source, still with millimeters marking arrow pointing up, but now we're gonna put it through a convex lens with a focal length of 200 millimeters or 20 centimeters. I'm gonna put this 30 centimeters away from my light source, and I'm gonna use this screen and I'm gonna find when it's most in focus. Well, that looks pretty good. We go right there. This is at the 90 centimeter mark, which means it is 60 centimeters away from the lens. So DI is 60 centimeters. And as you can tell, this is upside down. Oh, now you can tell. And it's bigger. I'm now going to do the same thing, moving my lens to the 40 centimeter mark. And I'm going to once again find when this is in focus. Looks right about there, which is at 80. So 80, I don't want 80 though, I want the distance from here to there. So that is 40 centimeters. And it looks the exact same size to me, but it's still upside down. We'll now move this guy to 50. Oh, there we go. As you can see, it's a lot smaller. It is reduced. It's still inverted, and its position is at 83, but this should be subtracted from here. So 33 centimeters. Once again, you're going to find theoretical values by comparing that to what you draw.